Hi, welcome. I am Jason Hall from ChainGuard. This is Jed Salazar from Adera, and we're here to talk to you about securing cloud-native applications. Let's get going. Yeah, are you ready? Are you ready for it? Are you ready for it, though? Okay, good, thank you. Needed one woo to proceed. I'm going to start off with a bold claim. Almost all of the vulnerabilities in your software are 100% avoidable. Yeah, bold, bold. I'm going to follow that up with another bold claim. All software is vulnerable eventually. So how do these two things both work together? It may sound like they're in conflict, but they're really not. I like to think, I lost it. No, I didn't. I like to think of software and vulnerabilities in particular as sort of this Venn diagram model. Software is the big outer one. We all know what software is, hopefully. If not, you are in the wrong talk. Software is unfortunately written by people, and people make mistakes. So the next level under software is bugs. Bugs are anything software does that was not intended to be that way. There are a number of things you can do to shrink the bug circle inside the software circle. You can write tests. I know it sucks, but you can. You can use a memory-safe language. You can do code reviews. There's a number of very, very good ideas for shrinking the bug circle inside the software circle, and you should do pretty much all of them. But bugs are inevitable. All you can do is shrink that circle, not eliminate it completely. Some percentage of those bugs are vulnerabilities. These are things that make your application vulnerable to an attacker and make your users' data potentially vulnerable as well. Okay. There are a number of things you can do to shrink the vulnerability circle within the bug circle. Again, code review, testing, memory-safe languages. And you can also do a lot to minimize the severity of the vulnerability if it's still there, things like observability, network segmentation, and many, many other things that you should do. And then the last category is 0 days. We'll talk about that in a little bit. So with that in mind, the number one thing you can do to reduce vulnerabilities is remove unnecessary software. Shrink that big circle. You probably don't need it all. If you shrink that big circle, you are shrinking all the other circles at exactly the same time. And that's what ChainGuard does with our minimal base images. We use the term distroless for this. This means generally images that don't need a shell don't include one. Images that don't need a package manager, and it's nearly all of them, don't get one. And only include what software, what dependencies you actually need in those images. So it wouldn't be a ChainGuard talk without the old comparison slide. We have on the left the Python latest image from Docker Hub. These are from, I think, 45 minutes ago when I made this slide. You can see that the Python image is much bigger. It contains many more packages, many more CVEs, and 10 critical CVEs compared to ChainGuard 0. We'll move on to the next one, which is Node latest and ChainGuard Node latest. Same story, smaller, 0 CVEs, 0 critical CVEs. And finally, Ruby, same story, much smaller, fewer packages, 0, 0. Now, the eagle-eyed among you might notice that the number of CVEs and the number of critical CVEs on these slides was actually the same. And you may have thought, wow, Jason just really messed up on these slides, didn't he? And I'm not going to fact check him, so I assume that's right. No, this is actually correct. They contain the same 583 CVEs and the same 10 critical CVEs because the Ruby image and the Node image both contain Python. And Python and all the stuff that supports Python in the image brings in many of the dependencies that bring in those 583 CVEs and the 10 critical ones that you should really be worried about. So the first thing we do is we can just get rid of Python in the Node image, in the Ruby image. You don't need it. If you do need it, you probably know why you need it, but if you don't know if you need it, you don't need it. So let's just get rid of it. But I will I'll continue with another bold claim. Distroless by itself is not enough. Just eliminating unnecessary software is an easy first step, is clearly something you should do, but in and of itself, it is not enough. My next bold claim is that known vulnerabilities are going to be a bigger threat to you than 0 days. And for that, we have to talk about what 0 days are. 0 days are the tiny little circle in the middle. These are unreported vulnerabilities. Generally, when somebody finds a vulnerability in code, they responsibly report it, and the upstream project receives that request and quickly fixes it. Generally, people don't like having vulnerable software, so they fix it, and they make a release, and all is right in the world. When they don't get responsibly reported, those are 0 days. The good news about 0 days is that they are expensive and rare. Generally, these are the purview of nation states trying to attack, large corporations. Generally, these 0 days are very complicated to exploit. It requires bouncing 6 or 7 things off of each other in just the right way just to get those things. I hate to break it to you, but you are probably not worth it. Your blog running on Kubernetes with 3 monthly viewers is probably not going to be, I know it's hard to believe. Your mom loves it, but the blog is just not what North Korea is after. There's even a website for all of the known vulnerabilities. It's run by the government, and they tell you everything about all of them. So known vulnerabilities are a lot more common and a lot easier to exploit for regular folks than all of these complicated 0 days that they write spy novels about. Your defense against the known vulnerabilities is shortening the window, is updating quickly when that upstream project fixes the reported vulnerability. And to do that, you have to choose a distro that prioritizes speed. So Wolfie is the Linux distro that backs all of the chain-guard images, and we pick up upstream releases, often within hours, sometimes within 1 hour, and build and release those and put them into our images. This is made possible with lots and lots of automation and hard work and tests, and we do it so that you don't have to. Unfortunately, this means it's still on you to update often. We can only produce images quickly for you. It's up to you to pick up those updates, test, validate, and do releases. Long gone are the days of the quarterly release, the monthly release, the weekly release. You should really be updating as often as possible to fix all these known vulnerabilities. And finally, I'll leave you with this. Vulnerabilities have a high cost even if you never get exploited. This is why CVE clean images are so important. It's hard to notice when you have 533 vulnerabilities in your image, when 534 get added, or 571, or 588. And your 11th or 12th or 13th critical CVE might not raise any alarms, even though it really should. If you do catalog your vulnerabilities, if you're keeping track of all of these things and watching them come in and go out, and regulated industries, many do, you're spending a ton of money to have somebody sit there and curate this spreadsheet of doom of all the CVEs coming in and going out, and was it fixed upstream, and is it really a thing? And that just on its own is costly and painful. So why not just not have the vulnerability? Can you imagine? Still, this is no silver bullet. Fixes take time to become available, even through chain-guard images. Immediate updates can be infeasible on your side for whatever reason. A shell, for instance, or a package manager may still need to be in the image, and so you can't debloat it all the way. And unfortunately, you still need to test your releases. But with that, I will give it over to my colleague, Jed. Take it away.
Hey, everyone. My name is Jed. I'm from Adara. We're new here, so hello, world. So as Jason mentioned, there is no silver bullet. That's essentially the point of this talk is, one is secure by design. Like, we want basically software that you don't have to deviate from the defaults. You don't have to flip a bit to be secure. Like, we don't want the, secure my ish flag. We want something to be secure just out of the gate. We want you to deviate from the default if you want it to be insecure. That's kind of the premise behind secure by design. And beyond that, there is no silver bullet. How many of you, just show of hands, run containers? Right. Are those containers isolated from each other? Aha, great question.
Mostly.
So we learned a lot about container images, and that is an absolutely essential layer in your stack. But shifting left isn't sufficient. It's not enough. We need to layer our security. The shift left was kind of presented at one point as the answer to security. And I think that most people have kind of recognized at this point that in and itself, it's not sufficient. You should be shifting left, and you should be thinking about scanning code and scanning for vulnerabilities, but that's not going to make your Kubernetes environment secure. So catching bugs earlier in the pipeline is a good thing. But really, I think what shifting left meant is that it put the entirety of the burden of security onto developers. And now we have terms like DevSecOps, which basically means that congratulations, you're not just a software engineer, you're now a security engineer as well. So yeah, that model unfortunately isn't really viable. In addition to that, there's a lot of problems with shift left if it's really your only, or even if you're depending on it for one of your main defenses, in that there's a lot of false positives. A lot of the vulnerabilities that come up are literally not legit. Most of them are not exploitable. And the difficulty of finding which ones are actually worth your attention, there's been entire blog posts written by ChainGuard and others about that. So don't shift in any one direction. Basically, security is too complex for that. If your business runs on top of Kubernetes, then it's sufficiently advanced and nuanced that you need to really think about security almost at every layer, which is never really a popular topic. Everybody wants the silver bullet, but it just doesn't exist. So this doesn't cover network policies, security monitoring, admission controller policies, using those images, using isolation. These are intrinsically good things, but don't throw these other things out. Use network policy. Admission controllers are crucial. You should be doing all of those things, basically. So this little pixelated Swiss cheese kind of advocates for the Swiss cheese security model. Has anybody heard of that? Basically, the concept is, you can kind of imagine an attacker trying to get through this, piece of Swiss cheese and kind of crawling through all of the different layers to get there. You have all of these defenses put into place in, minimal container images, but all of these other defenses are crucial as well. And the whole point behind this is that we really want to make our attackers' lives hell. We want to give them a bad day. If they want to come and own us, they're going to have to fight really hard to do it. And that's what we're building. So I'll give you an example. Let's say you do everything in your power to remove all vulnerabilities. You've completely shifted all of your container images over to ChainGuard images. All of your images are rebuilt nightly. You're picking up those fast patches, and you have low to no CVEs coming out of your scans, and shift left is all happy and everyone's good to go. But Kubernetes is a shared system. Clusters are shared between teams. Multi-tenancy isn't really the exception, it's the rule. Every Kubernetes environment that I've seen in the last 7 years is effectively a multi-tenant cluster. And not only are clusters shared between teams, but kernels are shared between containers. So when you're actually running your workloads on the Kubernetes node, they're all using the same shared kernel. And that shared kernel has access to all pod secrets. It's running the pod. It has basically full control over all of your workloads. So if another team with an image that isn't running an up-to-date distribution like Wolfie and has vulnerabilities, then all of your efforts to reduce CVEs and make shift left a success, with the right vulnerability, that won't matter because a single container escape can render your entire cluster untrustworthy, and you'll have to burn that infrastructure down and basically rebuild from scratch. So there are nuances here, and there are no easy solutions or no silver bullets. So I mentioned that containers have access to a shared kernel, and what we've talked about in this talk so far is basically the upper layers. Like we're talking about container images, we're talking about Ruby, Node, Python. Those are all things that are absolutely crucial. But containers also have access to a kernel. In fact, every container that runs in a Kubernetes environment uses the same shared kernel. And that's a pretty large attack surface. People, as a result, are starting to do some pretty crazy stuff that we've seen out in the wild to solve for this. There was a recent Kubernetes podcast episode where they talked about container security. And the guest said, in relation to container isolation, I never say isolation with containers. I say segregation because it's a shared kernel. Like, you can't build a sufficient sandbox if you have a shared kernel. If you have a shared kernel, then basically the best that you can do is segregating your workloads. Otherwise, basically all the one container gets compromised and it's game over for the entire cluster will remain true. So that's enough talk. Let me show you a demo on what we've been working on. So let's see here. Alrighty. Okay, so I might have to peek over here. Okay, so what we see here is that we're running a single node cluster. So there's not multiple nodes. I'm going to show basically isolation inside of a single Kubernetes node. So no magic parlor tricks here. We can see that we have this single node running in EKS. Now, recently we released a tool that helps people understand the difficulty of isolation with containers. This tool is called Am I Isolated? And the whole goal behind this is to help the community educate themselves on the problems around container isolation. This is a very nuanced topic. There's a lot of tests here. This is a initial release. You can grab this on our GitHub repo. I'll provide the link if you're interested. Come and talk to me. But what this does is it helps us understand, how open am I to a risk from container isolation. If one container gets compromised because someone's doing a bad thing on my cluster, what does that mean for me? So what we're going to do here is we're going to apply a standard pod. It's called leaky vessel. And like every Kubernetes talk, we're just going to apply the pod before we read the YAML, because that's the secure thing to do. But what is leaky vessel? Nothing really. It's not super interesting. It's a pod that has a couple of environment variables. One is specified in the YAML. The other is baked into the image. These are secret environment variables. So what does leaky vessel do? Well, if we take a look at the logs, it doesn't really do much. It's just sleeping. But we're going to apply, again, before we read the YAML, Raider. And Raider is actually a much more pernicious workload. So what is Raider? Let's take a look. Looks like a pretty innocuous pod spec. But with the right grep, we can see that what it actually is it has basically a couple of really dangerous flags. One is privileged. If you're unfamiliar, basically this means that we're not going to run as a container. We're going to run as a Linux process, effectively. Like we're running a process typically as root, unless you use chain guard. You're not using root by default. And we also are mounting in the host process ID, or the host PID namespace. So I like to quote Mr. Lewis here, who says that privileged is basically the most dangerous flag in all of compute. So let's see what we can do with this. So if we run psfo as expected, because we're effectively running this as privileged, we can see all of the processes running on the Kubernetes host. We're not contained. We are just seeing everything just as a standard Linux process. So what can we do with that? Well, we can do some interesting things. The container that's running, that's exporting its environment variables, because we have access to basically the shared kernel, we can grab the process ID of that container with some bash magic. And with that process ID, we can actually look straight into the shared kernel and find the projected environment variables. So these secret environment variables aren't so secret. And this, again, is a result of the fact that containers are using a shared kernel. And the real problem here is that this is fundamentally the way that containers are architected. There's no way out of this sans rewriting the kernel. So let's dive in and take a look at the secrets specifically. There they are, just a simple grep. So how are we going to protect this workload? Well, of course, we can just delete it. Let's just get rid of it and pretend that this never happened. But what we're going to do is, again, apply this pod. We're going to apply something called hardened vessel. And this is actually using this new Adara isolation technology. Let's take a look and see what the difference is between the leaky vessel that we looked at earlier and ours. Really ignore everything with the exception of the runtime class that's named Adara. What that runtime class does is it basically, when you run a pod, it runs it inside of its own isolated zone. If you want to talk about, in the questions like what the architecture looks like, I'm happy to do so. But it provides isolation from the shared kernel, has its own kernel. So every pod basically doesn't share a kernel, it runs with its own. So again, we'll just make sure that we are running hardened vessel. And we're going to go back to Raider and do the same thing, psfo. We see all the processes on the host. However, where's leaky vessel? In this case, we've gone to hardened vessel. So we're going to do the same grep. And we can see that because we're not using the same shared kernel, because we've actually isolated this container inside of this zone, we don't actually see anything from it. So that's how we've achieved isolation at Adara. Like, we're basically very new. But that's a quick preview of what we've been working on. And most importantly, that's us. Woo. Okay, if you want to play with any of the, let's see, how do I get back to the other screen here? Okay, yep. We are running a CTF, so for security enthusiasts who want to try and escape from this environment, we will be offering a modest bug bounty for those who are able to be confident in our architecture, but we love the community, and we basically want to improve container isolation and security across the board. You can find info at adara.link/CTF, or just come and talk to me after the talk. Thank you.
We have 5 minutes for questions. Okay.
I have multiple questions. I will start with one. We'll see if we have. Yeah. So we'll see if we have time. So most of the pods in Kubernetes that are using the privileged true flag or running in a host speed namespace are actually pods that are doing some infrastructure work on the cluster.
Yeah, CI.
Let's use the simplest example, Falco, as a runtime detection tool.
Mm-hmm.
How do you handle Falco? Because if you're separating it from the original host, then it won't be able to do any of its work.
Yeah, so each of it depends, right? Like if you're using eBPF, for example, for detection, we ship kernels for each of the zones, as we call them. So basically, you instantiate the zone, and then you give it a kernel so that it can run the container. You can ship that as an OCI image with BPF enabled. So you're still getting all of the data from that single container or maybe multiple containers per pod within that zone. And then you can take that data and just like, for example, something that looks like Tetragon or Sysdig, it'll use something like FluentD to just ship those logs out to some log sync, and then you can basically view the data from there. So it's really just shifting from like a shared kernel to a kernel per workload, and we can still get that same observability.
So if I understand, if you group together a number of workloads together under the same kernel, so in this case, Tetragon will see all the others in the same zone.
Yeah, so
but not the others.
So there's a kernel per zone, and there would be like a Tetragon instance running per pod in this instance. That would be observing basically one or more containers per pod, but it would only be observing the processes inside of that pod, inside of that one kernel.
Okay.
Great question.
How is this substantially different from, say, running KubeVirt?
Yeah, great question. KubeVirt is really meant to run virtual machines on top of Kubernetes. What that means is your virtual machine doesn't have isolation. It's running as a container, so any other containers that are running on that same system can access, the shared memory of that container. But it is running a virtual machine at the end of the day. What we're showing is basically, we're kind of Docker for, you could basically just run Docker run or really any container image inside of this environment. So we're running containers, but we're giving them the isolation of virtual machines, if that makes sense. So KubeVirt's like running virtual machines on top of Kubernetes. We're running containers kind of under the hood as virtual machines for isolation, but they're still containers.
Okay, thank you for this presentation. I'm curious to know if you can explain us, in this case, how the memory isolation works with Eldera.
Yeah, so what we saw earlier was when we looked at when we looked at proc, proc had all of those environment variables in it because it's a shared kernel. So each container that basically uses that same shared kernel is using shared memory. In our model, we actually have a kernel per pod. So it's separated by a hypervisor. So that hypervisor is completely isolated from a security perspective from the host. Like the host doesn't have access to the memory from that guest running in the hypervisor. And the opposite is true. Like the hypervisor doesn't have access to the host. So it's kind of a, you don't have to trust your provider and you don't have to trust the workloads that are running in your environment.
So kind of as a follow-on to the KubeVirt question, how would you distinguish this from something like Kata?
Yeah, absolutely. Kata requires virtualization extensions. So basically, your hardware has to support virtualization. And that basically means that if you're running in a Kubernetes environment, you're deploying your nodes on top of bare metal. And bare metal has a lot of negative consequences, like it's extremely expensive. They don't exist in every region, in every cloud provider. And they don't support auto-scaling. So the vast majority of the folks that we talk to are running on, say, EKS, using auto-scaling, and they want that kind of like, best price on a standard EC2 instance. So what you're looking at here is para-virtualization, so basically virtualization without needing support from the hardware. So we can run on, a standard EC2 instance or an edge device or even a Raspberry.
Last one. No? Okay. Thank you very much.
Thank you.
Thanks.